Hello everyone. Today we are going to discuss the continuation of the introduction of shears. So today's first topic is modes of failure due to shear. So if you consider any beam section, it will fail in different ways because of different reasons. So what are the ways or what are the modes of failure which we can see in the beams that we are going to discuss now? So majorly the failure due to shear is depend on the span to depth ratio, that is L by D ratio what we call, or insufficient shear reinforcement providing in the beam. These are the two main reasons which we can come across in the modes of failure due to shear. The shear failure is a sudden failure when it is compared with flexure. Flexure is nothing but bending. So in bending it will give certain warning to take precautions, but in case of shear the warnings given by the structure is not much as in case of flexure. So shear failure is brittle. It is a brittle failure. So the main reasons or the factors on which the shear failures depends are span to depth ratio, that is what I said, L by D ratio, and loading, whether it is moving loads or constant loads, UDL, UVL, and load intensity, all those things, combination of loads. Then cross section of the beam. Cross section means it is directly related with moment of inertia of the section. Then amount of anchorage reinforcement. Anchorage reinforcement means the arrangement which we are providing for holding the tendons after applying the pre-stressing force to maintain the stress in the tendons, tensile stress in the tendons. So for that arrangement we call as end blocks or anchorage devices. So in that case those end blocks will be designed and the sufficient reinforcement is to be provided to give the sufficient strength to hold the tendons, and so that is anchorage reinforcement. This thing we will discuss in next module we have. So now let us discuss modes of failure due to shear one by one. So first mode of failure is diagonal tension failure. So in this type of failure the crack propagates rapidly due to inadequate shear reinforcement. So diagonal tension failure is caused because of insufficient shear reinforcement. The stirrups what we call in the beam, so that is insufficient stirrups, or the spacing provided for the shear more than the required. So that is the main reason in which diagonal tension failure occurs. So the cracks formed in the shear will penetrate through the depth of the beam quickly. So that's what the warning will not be given sufficient time. So it will rapidly penetrate into the section of the beam along the depth of the beam. So the beam is, if you observe in the figure, the beam is gone, literally breakdown of the beam will occur. So the beam will split into two parts. So this is the example for failure due to shear, and this failure is called diagonal tension failure. So next type is shear compression failure. So in this, the concrete near the compression flange above the tip of the inclined crack. So that means the crack will penetrate from bottom to top along the depth of the beam. So obviously when deflection occurs, the top portion will be under compression and bottom will be under tension. So in that compression zone the concrete gets crushes at the end of the cracks developed from the bottom. So that is, it may be around in between flange, top flange and web. The inclined cracks will propagate through the web of the section, and crushing of the concrete will occur at the edge or end of the crack portion. So this is affected by amount of bending moment at the particular section. So it depends on the bending moment of the section. And crushing of concrete at the top flexure shear crack, then this type of failure is called shear compression failure. Next type of failure is shear tension failure. So first one is shear compression failure, and here we have shear tension failure. So in this, there is inadequate anchorage of longitudinal bars. The diagonal cracks propagate horizontally along the bars. When we are providing the longitudinal reinforcement, we will provide an hook at the end of the bars. If we provide only straight bars, there will not be proper anchorage for the reinforcement bars. So if we are not provided sufficient anchorage for the longitudinal bars, the cracks will develop from the bottom of the concrete and it will reaches the longitudinal reinforcement or longitudinal bars what we have provided in the section. And once it reaches, it will propagate horizontally towards the support. So when the crack develops at the edge of the beam, and it will penetrates up to the longitudinal reinforcement, and there onwards the crack will move horizontally towards the support, and the bonding between concrete and steel will get weakens. The strength of the bond reduces and the concrete and steel will get disrupted. So this leads to an anchorage failure. And this type of failure is called shear tension failure. So that's what anchoring, if we are not provided sufficient anchorage, the failure will occur, and this is called anchorage failure. Next type of the failure is web crushing failure. So here concrete web crushes due to inadequate web thickness. If the thickness of the web is not sufficient to carry the loads, so that is BW what we say, the web thickness, if it is insufficient, the concrete in the web portion will get crushes as the load increases, and thus the strength of the section or strength of the member reduces. So principal compression in the inclined direction and if the web is not strong enough, the concrete will crush due to principal compression. So this we can majorly observe in I sections. This type of failure, web crushing failure, is majorly observed in I sections. And last type of the failure is arch rib failure. So this type of failure is majorly observed in the deep beams, the beam which is having more depth, or if the L/D ratio is small, obviously the depth will be more. So in such cases the arch rib failure will occur. So the web may buckle and subsequently web crushes. Buckling of web may occur. This web buckling you might have observed in steel design. So the same concept we are applying here. The buckling of web may occur, or the concrete in the web portion will get crushes and loses its strength. So thereby the anchorage failure or failure of bearing. So at anchorage device, when web crushes, the anchorage also get weakens, the anchorage strength also get weakens, and failure of the bearing will occur. This type of failure due to an arch action within the beam, deep beam, is called arch rib failure. So these are the few modes or different modes of failures. So one is diagonal tension failure, then shear compression failure, shear tension failure, web crushing failure, and arch rib failure. These are the 5 important types of modes of failures in case of shear failures, modes of failures due to shear. So next topic we are going for limit state of collapse for shear. So what are the guidelines and what are the formulas we are considering, what are the parameters we are considering, and what are the formulas we have to calculate the shear force in the web according to IS codebook 1393, sorry 1343 1343 1980. According to that codebook, it has some guidelines to calculate the shear force. So what is that guidelines we have? So here, the shear studied based on the capacity of the section. So what is the maximum shear stress carrying capacity of the section? Based on that we are going to study limit state. So the capacity of the section consists of concrete contribution and the stirrup contribution. Obviously, when you are applying certain load on the beams, the concrete will carry some amount of load and later it will transfer to the steel, but in case of shear it will be transferred to the reinforcement, shear reinforcement, that is stirrups what we are going to provide in the beam. So shear reinforcement will carry some amount of shear force and concrete will carry some amount of shear force coming in the section. So that's why we have contribution of concrete as well as stirrups to carry the shear stress or shear force in the member. So VUR, it is the capacity of the section, VC is the concrete contribution, and VS is the stirrup contribution. So again, VC includes contribution from uncracked concrete, aggregate interlock, and dowel action. If we take concrete contribution, again it consists of dowel action and aggregate interlock strength and plain concrete capacity. So now the VC, shear stress carried by the concrete, depends on the whether section is cracked due to flexure. So 1343 gives two expressions to calculate shear stress carrying capacity of the concrete. So one for cracked section and another for uncracked section. So uncracked section will govern near the support and cracked section will govern at the mid span. But we need to go for analysis of both sections, support section as well as at mid span section. Then comparing both, we need to consider whichever is less. So for uncracked sections we have equations. VC equals 0.67 BD root of FT square plus 0.8 FCP FT. So in above expression we have the different parameters. B, breadth of the section if it is rectangle, and breadth of the web section if it is flanged sections. Then D is overall depth of the section. FT, tensile strength of concrete, that is 0.24 root FCK. FCP, compressive stress in concrete at center of gravity of concrete section due to pre-stress, P by A, effective pre-stress upon area of the section. Then the value of FCP is taken as positive, it is compressive stress in concrete, and reduced effective pre-stress needs to be considered in transmission length region of the pre-tensioned beam. So reduced effective pre-stress means the applied force will, we have studied losses of pre-stress at transfer at working stage. So at working stage means there will be some amount of loss of pre-stress will occur when compared to at transfer stage. So we need to consider the reduced effective pre-stress means the pre-stress which is occurring at the working stage condition. So that we need to consider. For a flanged section, when CGC is in flange, that is CGC means and neutral axis is in flange, the intersection of web and flange is considered to be critical location. the junction or the joint of web to the flange. That portion we consider as critical section. So the expression of VCO is modified by substituting 0.8 FCP with 0.8 into stress in concrete at the level of intersection of the web and flange. So what we will calculate FT, FB, we need to calculate that FB at the level of junction of flange and web. In presence of inclined tendons or vertical pre-stress, the vertical component of the pre-stressing force Vp can be added to VCO. So to calculate Vc, along with the above equation, we can consider vertical pre-stressing force if we are applying the vertical pre-stress. And for uncracked sections, we have one more equation. So previous one is cracked section. This is for cracked sections, and previous one is for uncracked section. So there is 1 minus 0.55 FTE by FPK into tau CBD plus mu naught VU by MU. So here VC is shear corresponding to flexure shear cracking. So we have two types of shear failures. One is flexure shear and another one is torsional shear. So here we are considering only for flexure shear. In this equation, the term 1 minus 0.55 FPE by FPK into tau CBD is additional shear that changes the flexural strength, flexural crack to a flexure shear crack. So this parameter will give additional shear in such that when the crack develops due to flexure will be converted into flax developed due to shear, flexural shear. So the notations in previous equations are as follows, what we have considered in previous one. So FPA, effective pre-stress in tendon of roll losses, what I said. So it will be less than or equal to 0.6 FPK. FPK, character strength of pre-stressing steel. Then tau C, ultimate shear stress capacity of concrete. This will be obtained from IS 1343/1980, table number 6. B, breadth of section for rectangle and BW for flanged sections. D, distance from the extreme compression fiber to the centroid of the tendons at the section considered. M0, moment initiating a flexural crack. MU, moment due to ultimate loads at the design section. VU, shear due to ultimate loads at the design section. The term M0 by MU into VU is a shear corresponding to the M0 that decompresses the tension force and initiates a flexural crack. The expression for M0 is given below, so it is 0.8 Ft into I by Y. So Ft is magnitude of the compressive stress in concrete at the level of CGC due to pre-stress only. An equal amount of tensile stress is required to decompress the concrete at the level of CGS. So CGS means the center of gravity of the steel or center of gravity of the tendon what you are providing. So the corresponding moment is Fpt into I by Y. So in the M0 equation, I is gross moment of inertia, that is moment of inertia of the entire section, and Y is the depth of CGS from CGC. So centroid of the concrete section to the centroid of the pre-stressing steel we are providing. The distance between those two is Y. So the factor 0.8 implies that M0 is estimated to be 80% of the moment that decompress the concrete at the level of CGS. Since the concrete and the inclination of the tendon is small away from the supports, any vertical component of the pre-stressing force is not added to VCR. So the factors 0.8 implies that we are considering only 80% of the moment at the level of pre-stressing steel, and inclination of tendon means there will be components, horizontal component and vertical component of the pre-stressing force, and we are neglecting the vertical component of the pre-stressing force, since it will be inclination is very small, that is theta will be small. The major component will be under horizontal and only minor component will be under vertical. So vertical pre-stressing force will not be added. So maximum permissible pre-stress to check crushing of concrete in shear compression failure, the shear stress is limited to maximum value of tau c. So tau c max. So the maximum value of tau c depend on the grade of concrete and is given in the table number 7. VU by BDT, it should be less than or equal to tau c max. So the shear force coming on the section, what we are going to calculate, that is VU by BD. It is similar one. So the shear stress should be less than maximum shear stress as given in case of table number 7 of IS 1343. So in this expression, dt greater of dp or ds. dp is depth of CGS from the extreme compression fiber and ds is the depth of centroid of regular steel. VU shear force at a section due to unlimited ultimate loads. So this is about introduction of design of shear for the pre-stressing members, and the guidelines will be given in IS 1343/1980. So in next classes we will start with problems on analysis of pre-stress as well as the analysis of shear stress in pre-stressing member and design of shear reinforcement for the pre-stressing members. Thank you.